So last time we talked about information sort of in the abstract. We sort of developed the notion of a bit, and then we talked a little bit about encoding information using bits, and thought a little bit about the actual information content and came up with a measure of the information content in a message. And we thought about how to remove the redundancy in our encoding to try to get our encoding length, our expected encoding length, to be about the same as the average information content in a message. So today we're going to switch from sort of the abstract notion of information to actually thinking about physical implementations of, in our case, circuitry that will allow us to represent bits of information and then store and transmit and manipulate them. So what are we going to do to actually create a physical representation of a bit? And, what would we like to have in a physical representation? Well, because the world is full of billions and billions and billions of bits, and in fact, your pocket is probably full of billions of bits, and then you can imagine how many there are by the time we cover the entire world with bits. I can always remember in chemistry reading about moles and Avogadro's number, and that always seemed the physical world, even in a small amount of space, had billions and billions and 10 to the 23rd things in sort of in the palm of your hand in terms of counting atoms. Well, bits are getting to be sort of on that scale in terms of their actual physical representation. The amount of space they take up is not quite at the atomic scale, but we're getting pretty close. So we want to be able to have a lot of them. We want them, in some cases, to be stable. Sometimes the period of stability is I'm only transmitting some information along a wire, so that representation only has to be good for the length of time, the speed of light or the speed of light along the wire. So we don't, our expectations is, on the order of picoseconds or nanoseconds or milliseconds, something like that. In your main memory system in your computer, the expectation is stability on the order of a few tens of microseconds, and then we refresh it. On the other hand, if you were an Egyptian pharaoh, your notion of stability in terms of the information that you were great and you want the world to know it for all time consists of building things that you hope will last for thousands and thousands of years. So you have to, when doing engineering, you have to sort of get all your specs in line so you can make the right choices. And finally, because our goal is not only to sort of chisel the message into a stone tablet and have it last forever, but we're interested in being able to transmit the message and store it in a variety of different media, and in particular do computations with the information. We want something that can be easily manipulated. And by easily, I mean that a small amount of dollars and power will let us do all sorts of magical things with information. And that might actually leave out stone tablets. Okay, information's been around for a long time, of course. Human beings have been about communication. In fact, that's one of the things that people often argue makes us human as opposed to belonging to some lower order. And in fact, we sort of measure, if you will, the degree of evolution by the amount of communication that's going on. And we always find ourselves surprised when, in theory, lower forms of life, I use lower in quotes because if anybody's read Douglas Adams and so long and thanks for all the fish, you sort of maybe appreciate we may not completely grok how well certain animals are, how intelligent they are, but the idea is that communication is sort of an essential component. So here, the sort of famous Boston communication, one if by land, two if by sea. So there's an encoding scheme there. And in fact, the message even contains a little bit of timing. In other words, no Landron meant we don't know yet. So, we've been having to solve representations of information ever since we sort of evolved into a species that found, painting bulls on cave walls was sort of cute and, informative, perhaps. So what physical phenomenon should we choose? Well, lanterns, that was great for Paul Revere, probably not so good for playing, World of Warcraft at home. Dominoes. How many of you have ever set up a really long chain of dominoes? It's both very fun and very stressful / frustrating, depending on whether they've fallen down yet or not. So here's a little representation of a logic gate that uses dominoes to, the sort of whether the domino is standing or falling determines whether there's sort of a 0 or 1 in that little region of space. And you can see the information as it travels across from one side to the other in the diagram. How about billiard balls? Well, here's a little representation of a fancy little piece of so-called reversible logic, in the sense that we can run it backwards as well as forwards, that does a little logic computation where now we're representing information by the presence or absence of a billiard ball. And as the information interacts with each other, in this case as the billiard balls bounce off of each other, where they come out will tell us a lot about what happened. And in fact, there's a whole branch of high-energy physics whose job it is to bounce things off of each other at the atomic level or the subatomic level, at the level of quarks and things like that. And by judging by what bounces out that they can detect, they can conclude a lot about what must have happened inside. But that's not very practical for the sort of MP3 encodings we have in mind. How about E. coli? The DNA is a very fancy and quite successful encoding of information. It trades off a little bit of perhaps short-term reliability for very long-term longevity. Millions and millions of years. We all carry around little bits of encoded information in the core of our cells that message was created, maybe 3-4 million years ago, or 3 or 4 billion years ago, maybe 3 billion. How long life has been around is sort of interesting. If you ever get a chance, you might consider reading The Selfish Gene by, oh God, now I'm going to embarrass myself. Dawkins. What's his first name? Richard Dawkins. Okay. How embarrassing. Anyway, I really enjoyed the book, even if I can't remember his name. But it talks a lot about, sort of information storage and how that might work in E. coli. We could talk about polarizing photons and communicate using, sort of an elementary particle, neutrinos perhaps in the future. So those last two have some potential application, and my guess is that in your lifetimes we'll be using both to store and manipulate information quite effectively, using both the biology or the chemistry of life, and then starting to use very small and fast particles to do our representations. But since we're electrical engineers, at least some of us are at least partly electrical engineers, we're going to use in this course things like voltages and currents and frequency and phase of signals to encode information. We're going to use voltages. And the reason we like voltages is that we can build a simple circuit that we can plug into the 110 volts on the wall that will produce basically a large supply of high current supply for both 0 volts and some power supply voltage, 1 volt or 2 volts, whatever we choose. We have a lot of engineering knowledge. We've been engineering with voltages now for more than a century, and we understand a lot about all the technical details. And as we'll see, not this time, but next time, we have a way of, if we're not actually manipulating the information, if it's just sort of sitting there quietly, sort of in storage mode, we can design our circuits to dissipate basically no power. And that's why things like your cell phone batteries and your digital watches, they last for a day or a year or something like that. Well, that's important to us. And so we've learned enough about how to manipulate voltage encoded information that we can sort of spend power only when we need to. Now, there's some disadvantages to voltage, some of which we'll meet today. Mainly, it's easy to be corrupted by other physical phenomena around us. So any other sort of moving currents in nearby Conductors will often create changes in voltages on a wire I'm interested in, and we'll have to sort of think about how to engineer around that. And in fact, one of the big messages of today is that we do have to take into account the real world at this low engineering level. We can't afford just to be abstract and mathematical. We have to deal with the fact that bad things happen to good voltages. So, so we'll be concerned about that, and we'll fix up our engineering so that we will get what we want despite bad things happening.